In the previous lecture, we have seen the classical wave equation. In fact, we have found the classical wave equation in 3 dimension and also in 1 dimension and 2 dimension. And as I have told you that in the forthcoming lecture, we will see the solution of the classical wave equation. So today we are going to see the solution of classical wave equation, and in this regard, in this first lecture, I am giving you the solution of one-dimensional wave equation. As you know, the one-dimensional wave equation is given as in this way. This is del 2 psi by del x square equal to 1 over v square del 2 psi by del t square. You know here psi is the wave function, which will be actually a function of a space coordinate x and time t, and v, this is actually the phase velocity of the wave. As you can see, this is a partial differential equation of second order, and you know the partial differential equation can be solved by transforming this equation into ordinary differential equation. And for this, we apply the technique of method of variable of separation. And so we will use the method of variable of separation to solve this equation. As you can see that this psi is a function of x and t, so to apply the method of variable of separation, you know we will express this wave function psi of xt as a product of two functions, and in those two functions, one will be only a function of x and another will be only a function of t. So I have expressed here the solution psi of xt equal to capital X of x times capital T of t, or you simply say that psi of xt equal to x times t, where x is a function of only the independent variable small x, that is space coordinate, and capital T is only a function of t. Now we will use this equation 2, that is psi equal to xt, in equation 1, and you can easily see that this del 2 psi by del x square will be what? This will be simply t d2x by dx square, and del 2 psi by del t square will be x times d2t by dt square. And so you can equivalently write it as 1 over x d2x by dx square equal to 1 over v square t d2t by dt square. One thing here you can see that I have not used the partial differential symbol, but instead of the partial differentiation I have used actually the ordinary differentiation. Why? You know, as this capital X is only a function of a small x and capital T is only a function of a small t, so x and t are functions of only one variable. And when a function is a function of only one variable, there is no difference between the ordinary differentiation and the partial differentiation. So I have used the symbol d dx instead of del x. Now you can see this equation 3 that variables are already separated. In LHS you can see this is only a function of a small x, and the RHS is a function of only a small t. So variables get separated, and you know if LHS is a function of a small x only and RHS is a function of a small t only, and x and t are independent variables, then for all values of x and t, this equation 3 will be satisfied only when each side of this equation will be equal to the same constant. So let us set each side of this equation equal to same constant. So you can say as LHS is a function of X and RHS is a function of T. Function of T. So for all values of X and T, this equation means equation number 3. Equation 3 will be satisfied. Will be satisfied only when both sides of the equation will be equal to the same constant. Actually, this constant is known as constant of separation. So let us put here that the LHS 1 over x d2x dt square is equal to lambda, where lambda is separation constant, and equivalently you may say that this d2x over dt square is equal to lambda x. And again you can see 1 over v square t d2t by dt square. This is also equal to lambda, and this implies that this d2t by dt square will be equal to what? This will be v square t times lambda. V square t times lambda. Say this is equation 4. Now for seeking the solution of this equation, you can see there may be 3 possibilities, or you may say that there are 3 possibilities here. So there arise 3 possibilities. What are those possibilities and which possibility is actually possible? We will discuss it. So let us consider the first possibility. In first possibility, we consider that the separation constant is 0. So let us take lambda equal to 0. So if lambda equal to 0 we assume, then what will be our equation 4 here? You can see we will set lambda equal to 0 in RHS in both equations of 4. So in this condition, so you can say so that by equation 4 d2x by dx square will be equal to 0, and we may write it as dx dx, and this equal to 0. And therefore, to know the value of x, we will integrate it, and so you can see the integral of dx by dx will be what? This will be integral 0 dx. And you know, integral of differential of a function is simply equal to that function. So here we are integrating the differential of dx by dx. So this integral will be simply dx by dx. And integral of 0 will be equal to 0 plus some constant. And let us consider this integration constant is a. So this a is actually integration constant. So you can see our result is dx by dx equal to a. Now to get the value of x, we will again integrate it, and you can see integral of this dx will be equal to a times integral of dx. A is constant, so I have taken it outside of the integral, and you can see this integral will be simply capital X of x is equal to a times a small x plus another integration constant. And let us say this another integration constant is b. And so this equation is 5a. So here a and b are arbitrary constants. Actually, these are integration constant, as you can see. And similarly, when you will integrate the second part of this equation number 4, you can see there will be no difference. Equation will be d2t by dt square equal to 0. So only instead of capital X, there will be capital T, and instead of a small x, there will be a small t. So you can write the solution of that very equation directly by seeing this solution. So I am not going to write all the steps, but by analogy or by induction, I am writing directly the solution of that part of the equation. So again, you can see that our equation will be d2t by dt square equal to 0, because lambda we have taken equal to 0. And therefore, in the light of the above solution, you can see that this will be t of t equal to an arbitrary constant, let us say here c, times t plus another integration constant capital T. So these are the solution of the wave equation when we consider that our separation constant is 0. In fact, after a little while, we will check this these solutions are valid solution of wave equation or not. But I am till now I am considering only the different possibilities. We will test that these solutions are valid solution or not valid solution some time later. So now let us consider another possibility. We consider that lambda is equal to a positive quantity, and if it is positive, you can express it as a square of a quantity, because a square is always positive. So let us say lambda equal to mu square, let us say. So you have taken lambda as a positive quantity. In fact, when we will consider that lambda is equal to positive and this is equal to mu square, then what will be our equation? You can see that our equation was in fact d2x by dx square equal to lambda times x. And here we have considered that this lambda is equal to a positive quantity which is mu square. So this is d2x by dx square equal to mu square into x, and equivalently you may write it as d2x by dx square minus mu square x equal to 0. And similarly, you can write the solution of another part of the equation, seeing this not solution but the form of the equation. So again, let us say this is equation 6a. Again, we will write d2t by dt square. You have seen that this d2t by dt square is equal to what? This is in fact equal to v square t times lambda, and I have considered this lambda as mu square. So let us put this lambda equal to mu square. So this will be equal to mu square v square into t, and equivalently you may write it as d2t by dt square minus mu square v square t equal to 0, and say this is equation 6b. Now you can see that the form of equation 6a and 6b, as you know, from these forms of the differential equation, the solution will be actually exponentially varying. So these are the standard equation. In fact, in the beginning of this topic, boundary value problem, I have discussed the solution of ordinary differential equation and some of the special functions, what you will write the solution of different forms of a standard differential equation, I have already discussed. So in the first lecture. So on the basis of those ideas, I am just now writing the solution of equation 6a and 6b. So you can easily see that solution of equations 6a and 6b are given as. In fact, solution of 6a will be what? X of x equal to an arbitrary constant a, e raised to the power mu x, plus another constant b, e raised to the power minus mu x. So this is in fact equation 7a, and the solution of another equation you may write this is c, e raised to the power mu vt plus d e raised to the power minus mu vt. You may check that these are the valid solution of equation 6. Simply differentiating these two equations 2 times, you will get the equations defined in equation 6a and 6b. So this is our second possibility, when we have considered that the separation constant is lambda is equal to a positive quantity, and that is equal to mu square. Now I am talking about the third possibility. In third possibility, we will consider that separation constant is negative. So lambda is in fact negative. And if you consider that lambda is negative, then you may take lambda equal to minus mu square, because mu square will be always positive, so lambda will remain always negative. So if you take lambda equal to minus mu square, then what will be our equation? You can see in this condition, the first equation will be d2x over dx square. You can see that only sign will be just changed. Here in equation 6 there is minus mu square x square, and so now it will be plus. And also in equation 6b here will be plus. So our equation in this condition will be d2x by dx square plus mu square x equal to 0. Say this is equation 8a. And the another equation will be d2t by dt square plus mu square v square t equal to 0. And this is 8b, let us say. Now you can see these equations are simply the equation of oscillatory motion, or you may say this is equation of simple harmonic motion, that is SHM. So definitely the solution will be an oscillatory function, and this oscillatory function in most general form is written in the form of e raised to the power plus minus I mu x, or you may write its solution as a combination of sine and cosine function. So solution of 8a and 8b are oscillatory. You can easily see oscillatory. So you may write x of x equal to a e raised to the power I mu x plus b e raised to the power minus I mu x. And similarly for t, you may write t of t equal to constant c e raised to the power I mu vt plus d e raised to the power minus I mu vt. And what is the equation number? This is in fact 9a, and this is 9b. You can also write these solutions in terms of the sine and cosine function. So, or you may say these solutions can be given as x of x equal to a cos mu x plus b sin mu x. Say this is 10a, and t of t, this will be equal to c cos mu vt plus d sin mu vt. You may write it in this way. Now actually, to evaluate the arbitrary constants, we use the proper boundary conditions. And for this, let us consider a proper example of the one-dimensional wave. For this, let us consider there is a string fixed at its two ends rigidly. Let us see this string is fixed at points P and Q. And let us consider that we slightly pluck this string at any point, or you can say in the middle of its length, in a direction perpendicular to the length of the string. So a transverse wave, you know, is set up in it, and that transverse wave travel along the string which lies, let us consider, in x direction. So a one-dimensional transverse wave traveling in x direction is produced in it. In fact, after plucking, the shape of the string will be like this. You can see the shape will be like this. So the string while vibrating will be like this, and a transverse wave is set up, and that wave travels in x direction. Now consider that here x is equal to 0 and here x is equal to L. It means the length of this string is equal to L. So x equal to 0 and x equal to L at both ends. And in this case, actually, the displacement of any segment of the string acts like just the wave function. So if you consider here that displacement is psi, then this psi is actually the wave function in this case. Now you can see from this actual problem what will be the boundary conditions. So what are the boundary conditions for the evaluation of the arbitrary constants? You can now see easily from this example. So first of all, we will note the boundary conditions. Boundary conditions. See, the first boundary condition, you can see that at x equal to 0, always the displacement is 0, and similarly at x equal to L, always the displacement is 0, because the string is rigidly fixed at the ends x equal to 0 and x equal to L. So the segment of the string at x equal to 0 and x equal to L never get displaced, and so psi is always 0 at all time at x equal to 0 and x equal to L. So you may write the first boundary condition in this way, that the displacement at x equal to 0 at all time t is equal to 0. It is equal to 0. And the another condition will be psi at x equal to L at all time t is always 0. So this is actually the first boundary condition. You can see from this example, since the segment of the string at x equal to 0 and x equal to L never get displaced, so definitely this displacement psi, which acts here like a wave function, remains 0 at all time t at x equal to 0 and also at x equal to L. So this is the first boundary condition. Now again you can see what is the second boundary condition, or you may say the initial condition. In fact, psi at x equal to x and time t equal to 0. This will be actually, you have seen that it is only a function of x. While deriving the classical wave equation in the first lecture, I have shown that this displacement at t equal to 0 is only a function of x. And at the same time, you have also seen that this del psi by del t, this is actually particle velocity, and this del psi by del t at t equal to 0, this will be also a function of x, and let us say this is a function of g of x. So this is our second boundary condition, or you may say initial condition. Now you have seen the solution of our wave equation in one dimension. I have written in the beginning here that this solution psi of xt is equal to x of x times t of t. In fact, this solution holds for all values of x and t. So when we will in fact take x equal to 0, then this equation will hold. When we will take x equal to L, then again this equation will hold. So on the basis of this equation 2, now let us impose the first boundary condition on it. So now you have already seen that psi of xt is equal to what? This is x of x times t of t. And therefore, if we consider that x is equal to 0, so we will write psi of 0t, then this will be x of 0 times t of t. But you have seen that this psi of 0t, according to this first boundary condition, this is actually equal to 0. So you can say that this is equal to 0. And again, you can see that psi at x equal to L and time t will be what? This will be x at x equal to L times t at t. But you have also seen in the first condition that this psi is again 0 when x is equal to L. That is, we are talking about the second end of the string. So this will be again equal to 0. So what actually these result implies? In fact, these two results implies that either this t of t will be equal to 0, or x of 0 will be 0 and x of L will be 0. Anything may be possible. So you can say these results imply that either t of t equal to 0 or x of 0 equal to 0 or x of L equal to 0, because the product of these two functions are always 0. So from these results we conclude that either t of t will be 0 or x of 0 is 0 or x of L is equal to 0. So in this condition, when we will actually apply these results in the equation, let us see the equation which I have mentioned here, that is the first, in case of the first possibility. So see the results of first possibility, that is when we have taken lambda equal to 0. So you have seen when lambda is equal to 0, then x of x is equal to ax plus b, and t of t is equal to ct plus d. So now we will use these conditions in that equation. So you can see now when lambda is 0, then what was our result? We have two results actually in this condition. X of x was equal to ax plus b, and t of t was equal to ct plus d. So now we will impose this the conditions which we have obtained here in these equations. So you can say when x is equal to 0, then x of 0 equal to a into 0 plus b. Actually, I have used this condition here, and as you know, x of 0 may be 0, so this will be 0 equal to b, and so this result implies that the constant b is equal to 0. Constant b is equal to 0. And again, you have seen that when x is equal to L, then again it is 0. So x at x equal to L is again 0. And so when you will take x equal to L, see this equation, then this will be AL plus B equal to 0. But we have already proved that this constant b is equal to 0. So this will be AL plus 0 equal to 0, and it means AL is equal to 0. And as you know that L is the length of the string, and this cannot be 0. And so if L is not 0, then this result shows that this constant A will be equal to 0. So what you get from this result? In fact, if we will take lambda equal to 0, then both of the constants will be actually equal to 0. That is, both A and B are 0 in this condition. Now, again from equation which we have obtained in the second possibility, when we have taken lambda is equal to a positive quantity. So in that condition, what we will get, let us see now. So see the second possibility, the results of the second possibility you see. So you have seen that when lambda is equal to a positive and this is equal to mu square, actually in this condition we have obtained two results. You can see the results obtained earlier, that this is A e raised to the power mu x plus B e raised to the power minus mu x, and the another result was T of t equal to C e raised to the power, what was our result actually, e raised to the power mu vt plus d e raised to the power minus mu vt. This was actually our result when we have taken lambda as a positive quantity and that equal to mu square. So now let us see when x is equal to 0. When x is equal to 0, then see from this equation, this will be x0 equal to A e to the power 0 plus B e to the power 0, and this will be simply equal to A plus B. X of 0 equal to A plus B. But you know that this x of 0 is equal to 0, as you have seen here, that x of 0 is equal to 0, you have seen. So let us put x of 0 equal to 0, and so we will have A plus B equal to 0. A plus B equal to 0. And again you can see when we will take x equal to L, then x of L is equal to what? Let us now put x equal to L in this equation. You can see this will be A e raised to the power mu L plus B e raised to the power minus mu L. But you have also seen that this x of L is equal to 0. So you can say that this A e raised to the power mu L plus B e raised to the power minus mu L, this is equal to 0. So now you can see, since A plus B is equal to 0 and A e to the power mu L plus B mu e to the power minus mu L is equal to 0. So from these results we conclude that A is equal to B and that will be equal to 0 only when for all values of L this equation will be satisfied. So in fact in either of these two cases we find that the constants A and B are equal to 0. So you can see what is the conclusion of these calculations. So you can see that in either case, when you say either case, that is when lambda is 0 or lambda is positive, we have considered these two cases. In either case, A equal to B and this equal to 0. And this gives, if A and B will be 0, then what will be x of x? Let us see. Since x of x you know is equal to ax plus b, or x of x is equal to a e raised to the power mu x plus b e raised to the power minus mu x. Actually, in case of first possibility, when lambda was 0, then this was our result, and when lambda was actually positive, then this was our result. But we have obtained that in these two cases both constants A and B are 0, so you can say that for all values of x, capital X will be 0. Capital X will be 0. And if this capital X is 0, what actually this result indicates? You can see that the solutions defined here and here fail to give the solution of equation 1, and it is the solution, it will be the next solution, that is the possibility number 3, that will be actually valid. So x of x is equal to 0 in all these cases. So the possibility that lambda equal to 0 and lambda equal to mu square, that is positive, are not valid as these can not give the solution of wave equation del 2 psi by del x square equal to 1 over v square del 2 psi by del t square. Because in this condition, if you consider lambda equal to 0 and lambda equal to mu square, then for all values of x, this capital X will vanish, and if capital X vanishes, then you can say that this psi of xt will be 0. Why? Because you know psi of xt is equal to x of x into t of t, and as we have proved that this x of x will be 0 for all values of x, so this wave function will be 0 for all values of x and t. So we can say, since the wave function is 0 for all values of x, it is not a valid wave function. So definitely our supposition that lambda is either 0 or lambda is either positive is not a correct supposition, and so this possibility is not valid. So definitely if these two possibilities not valid, so certainly the third possibility will be valid. And our third possibility is what? You know, the third possibility is actually lambda is equal to negative, that is minus mu square. And so definitely in this condition, the solution which we have written here will be actually the valid solution. So you can say that as the solutions which we have defined in case 1 and case 2 fail to give the solution of wave equation, and it is the so then actually these solutions defined in equation 9a or 9a and 9b or 10a and 10b, in which you can see that x and this capital T varies periodically in time and space. This will be actually the solution of our wave equation. But for simplicity, I am dividing this lecture in two parts. In fact, in this first part, I have discussed only the first two possibility, and you have seen that the first two possibility actually does not give the solution of the wave equation in one dimension. And so we have concluded that the third possibility, when we consider that separation constant will be negative, will give the actual solution of the wave equation in one dimension. But that solution we will discuss in the next lecture. And so I suggest you definitely, when you will watch this video, definitely watch the second video after this, because in continuation this problem will be completed. So when you will watch this video and the video which will come after this, then actually the solution of wave equation in one dimension will be completed. So must watch both of the videos in successive manner.